Log on, tune in, find out. Another good idea from Cambridge.
Morning session of the workshop. It's a great pleasure to our first speaker, Premet from Manchester. He'll talk to us about modular Lie algebras in the Gelfand-Kirillov conjecture.
I would like to thank the organizers for inviting me to take part in this program and for giving opportunity to speak. So I'm going to talk about the Gelfand-Kirillov conjecture, which many people abbreviate like this. And it was formulated in 1966 in a paper by Gelfand-Kirillov, published in Publications Mathématiques. And they called it fundamental hypothesis. So first of all, we let K be an algebraically closed field of characteristic 0. And then we can define, it's supposed to be bold-faced, an of K is a nth Weil algebra over K, so it's generated by some variables and partial derivatives over K. And then we have a polynomial algebra in, say, R variables, maybe. And then we define in R variables, after which we can define A and R to be over K to be this tensor product over this polynomial algebra. And so this is a Noetherian domain because it has a filtration as the corresponding graded algebra is a domain, commutative domain. So now we have also enveloping algebra of Lie algebra L. So L is an algebraic Lie algebra over K, and U of L enveloping algebra which is also a domain, an Noetherian domain. So the corresponding graded algebra is a polynomial algebra. And then once we have this, we can form the fields of fractions for both. So and we define Z and R to be the skew field of fractions of A and R, K, and that's what the conjecture states, that it states the following, that the field of fractions of the enveloping algebra is isomorphic to Z and R, maybe I should put of K, for some N and R. And one can later specify what these numbers are. They come from a coadjoint action of the group on L. So the conjecture is very general, and actually it was stated over arbitrary field of characteristic 0. So this assumption wasn't mentioned. But then in early 70s, it was pointed out that one has to add this assumption, otherwise the conjecture just fails for some small dimensional solvable Lie algebra.
Sorry, what is an algebraic Lie algebra?
Yes, I should say algebraic Lie algebra is a Lie algebra of an algebraic group. There are two closely related notions. Some people call Lie algebra algebraic if it has a Jordan-Chevalier decomposition or separating. So these are closely related things. So this conjecture is very general, and so Gelfand-Kirillov proved this conjecture. So they proved it for the first case when L is nilpotent. In the same paper, and more interestingly, in the case when L is GLN or SLN. So this sorted out the case of simple Lie algebras of type A, and the proof relied on the fact that they used the fact that in a crucial way that SLN has a parabolic subalgebra of codimension equal to rank. So in this case, n minus 1. And that's a very special feature of type A. And some people call the parabolics like that mirabolics. So they don't always exist. And so the question remained: when is this conjecture holds, and when it doesn't hold. But first, let me explain what are these algebras, just a little bit. My problem with this conjecture was that I didn't quite understand how the whole thing works. So when we have A is a Noetherian domain, so Noetherian is very important. Then A is what is called an ORA set. So then we can have the following. So take non-zero elements A, B in A. And then so this argument actually goes back to Gelfand and Kirillov. It's very elegant. So we define IA as a left ideal generated by A, B to the power n. And then we get a chain. So we have I0 is contained in I1, is contained in IN, and so on. So this should stabilize. By this assumption, so therefore we may assume that IM is equal to IM plus 1 for some m. And then we can express A B to the m plus 1 as which lives in this ideal as a summation of some xi A B to the power I runs from 0 up to m, because these ideals are equal. Of course, so this starts with x0a, that's crucial, plus x1b plus so on. But this x0 doesn't have to be non-zero. However, now we use the second assumption that A is a domain, and therefore, since A and B are both non-zero, this is also non-zero. So there will be at least one non-zero summand. We take the first one, and then we can cancel sufficient power of B. So then we can reduce to the case where x0 is not 0, just by this cancellation. And then a wonderful thing happens. Then we can have x0 be, maybe I should close this. X0 be is x0a is equal to y0b for some non-zero x0 and y0. And so this means that we can make sense of the symbols. This implies that we can make sense of the expressions u inverse v, where u is non-zero. So we can form these fractions, and then we can multiply these fractions. So we can say u inverse u1 inverse v1 times u2 inverse v2, and then we can use this thing, and we can find an elements u3 and v3 such that this thing is equal to this. So we can replace, as in the commutative case, but of course we pay really large price for that, a huge price. We need to go through all this routine and to find u3 and v3. This is not a commutative situation. And so then this will become, and this is again in standard form. So this happens, so we can localize Noetherian domains and also more generally prime Noetherian rings by using some sets which are called torus sets, which the definition is here on the board. And then the localization has very nice properties, but what I was trying to say is that computing in these localized rings is nearly impossible, because to multiply these two fractions here, we need to find u3 and v3, and so we now form this chain of ideals. We want to find when this ideal stabilize. We need to find, so no computer would help you to do this, I think. So computing is impossible. And so I thought maybe these things are useless, and why one should be interested in this conjecture for quite a long time. But now I know the reason why one should be interested in this conjecture. So these rings here are not, from my point of view, they're not here for computing, but they're here for reducing mod p. So, and then when you reduce mod p, you need to know at least something about fractions. So the commutative case tells you the general philosophy is that when you localize, things simplify. But in this case, well, this shows you they not really simplify in a sense. They become more complicated. But Gelfand and Kirillov realized that they simplify in the following sense, so that defining relations simplify. So defining relation of the localized object should be simpler than those for the original object. And they stated the conjecture in the sense that defining relations are as simple as they could possibly be. But that maybe was a bit too optimistic. Now, how can one make use of this conjecture? Why is it actually useful? So let me try to explain. It's not going to be maybe very convincing. So we take now G is a simple Lie algebra, well, finite dimensional simple Lie algebra. And then we can base change from a Chevalier form so we can obtain this in this way. This is the Chevalier form. Right, and now we take a primitive ideal of U of G, of the enveloping algebra. One wants to understand, well, what this is. One can show that this is defined over finitely generated Z algebra. Well, simply because it is Noetherian. And, but that's not good enough. Say that algebra, let's call it A. One can actually localize it. The reason is that the corresponding gradient is is an ideal of a gradient ideal of the symmetric algebra S of G. And so we can use the gradient version of generic freeness theorem, for example, in Eisenbut's book. It's not so easy to find a statement that we need here, but it does exist. So, and it tells you that we can actually localize, take a finite localization of this algebra A, and all graded components will become free over this localization. It's just a finite localization. So we can assume, in this case, we can assume that Gi and therefore also I, and also U of G by GA by, I should probably add this indices here, are free A modules. Free A modules. And then we can reduce mod P. So then we can look at IK. K is the algebraically closed field of characteristic P. Such that we do have a reduction for our ring. There are infinitely many primes available. And then we define this to be IA tensor over A by this field. And this is an ideal of U of GK, which we can also base change. So, of course, it's not going to be primitive because the way we did everything is the rate of growth of all these homogeneous pieces will be exactly the same as in characteristic 0. Nothing has changed, but we are now in characteristic P. And so I have a conjecture here is that conjecture. This would have some important implication. Conjecture is that for all P sufficiently large, the ideal IP, which is just this, maybe IK, I should say. So is prime. Is prime. So for almost all primes, we can do this. We can get from a primitive ideal in characteristic 0 an ideal in characteristic P. And the question is this prime or not? If you look at the commutative case, in the commutative case, actually, this problem was addressed in the 20s by Amy Noether. And she proved in commutative situation, actually, this holds, at least for number fields. And this was later reproved and generalized by Shimura in the 50s. So in the commutative case, this actually is true, and there is a hope, and maybe it would be true in general, though it's difficult to prove. And the approach to the proof would be via localization. So we can take S, or we can take, say, A to be, no, A is already engaged, maybe R, to be U of G divided by this primitive ideal. And this is a prime Noetherian ring, so S is all non-zero divisors. And by Gold's theorem, this is an ORA set, and definition of ORA set is over there. So we can still localize exactly as we did before. And then by Gold's theorem, this localization is a matrix algebra over matrices of some size, say D, over some division algebra, D. So this is called the Gold's field. Gold's field. And this D is the Goldie rank of the quotient. And so in type A, Joseph proved that this is only true in type A. This D is actually something that I already introduced. So some dk ds of k for some s. So it's a fraction ring of a Weil algebra. And one can say that what this S is for some S. S is 1/2 of the dimension of the associated variety of this ideal. So the smaller this ideal, the larger these D's. And then if we know that this is true, we know, and the Weil algebra has a very nice property from this point of view that I mentioned before. When we reduce, of course, we cannot reduce D mod P, but we can have something inside this, something finitely generated, say some algebra R, and this is still finitely generated, which we can, over some ring, which we can reduce mod P. So can reduce mod P. And since we know that this is a Weil algebra, there is a hope that this still will be prime. Because we know that when you reduce a Weil algebra mod P, it is still a prime ring. This is very easy to prove. So at least we need to know something about this here. So we need defining relations for D to be able to do this. So one can actually make sense of Gelfand-Kirillov conjecture after all. It can be useful. So there are some partial results related to this conjecture. Maybe I will mention a few of them. First of all, there was work by Borjo, Joseph, independently, and McConnell in the 70s. So they proved, independently proved Gelfand-Kirillov conjecture for solvable Lie algebras. So in the 70s, studying solvable Lie algebras was quite popular, and also primitive ideals, because a representation theory of solvable Lie groups was being developed at this time. Now it's not so popular, but so we do have this result. And there was also interesting work by a former PhD student of Jacques Dixmier and Guillaume, and so he proved the Gelfand-Kirillov conjecture for some natural semi-direct product, which actually occur in the simple algebra case. For example, in this case, so when we have the symplectic Lie algebra, SP to n, it acts on a vector representation, which we regard as an abelian ideal. And this is really almost the centralizer of a long root vector. If you factor out this, the line spanned by this nilpotent element, then you get this Lie algebra. So this may be relevant for Gelfand-Kirillov conjecture for SP to n plus 2. So the conjecture holds in this case. And there was a result by Gelfand and Kirillov in the simple case. So one can form an extended enveloping algebra, so we can do U of G tensor with over the center of G. Z of G is the center of this enveloping algebra. We tensor it by U of Cartan. Now we need to know how this actually acts on that. it acts via Harish-Chandra homomorphism. So, and this is a very nice ring. It is still a prime ring. In fact, it's a free module over U of G, which is a subalgebra here. Because of the module of coinvariance is free. And so, so one can formulate, since it's prime, one can formulate a version of Gelfand-Kirillov conjecture for this extended algebra. And so that GK is true for this extended thing. But we're interested in the non-extended case. It is not known even for SP4. So, well, at the moment. And at the other extreme, there was a also well-known paper by Kohns. So this states basically exactly the opposite. So one can take I to be the annihilator in the enveloping algebra of a Verma module M lambda. Even in the case when M lambda is reducible, this I is a primitive ideal, and it's a minimal primitive ideal. So by Duflo theorem, so I is generated by its intersection with the center, which is a maximal ideal of the center. So basically by the central character. And then we can look at U of G mod I, and this is also has a filtration. The corresponding gradient algebra is, because of what I said, is just the function algebra on the nilpotent cone. So is a domain. And then we can formulate a version of the Gelfand-Kirillov conjecture in this case, and it is true. So this is of Gelfand-Kirillov type. So GK holds for this. So exactly the opposite version. But then eventually a conjecture was disproved by for some semi-direct products. And that was in the 90s. So in 1996, there was a paper in Transactions by Aleph, Ooms, and Vandenberg. So, and they showed that that the Gelfand-Kirillov conjecture fails for some semi-direct products. Semi-direct products. Semi-direct products of the form GL equals G acted on the G module V, and V is regarded as abelian ideal. And that doesn't have to be irreducible. G is simple. So the smallest case is when this fails and dimension of L is 9. In this case, G is SL2, and V is direct sum of two adjoint representations, V2 plus V2. The 2 is highest weight. So in this case, a conjecture fails, and in many other cases. And later, Ooms and also Aleph, Ooms, and Vandenberg proved the Gelfand-Kirillov conjecture holds if dimension of L is less than or equal to 8. So in this case, so 9 is the critical number in a sense. But this mystery still remained for simple Lie algebras. So it's not how can one do simple Lie algebra. So now there are some new algebras around which many people like, some people don't like very much. But so one can still formulate Gelfand-Kirillov conjecture of them. For example, finite W algebras. So the finite W algebras, there will be more on it in Lossov's talk tomorrow. So let me not define these algebras. So they depend on a nilpotent element E in a simple Lie algebra G, and they also are non-commutative polynomial algebras. They have nice filtrations. The corresponding gradient is a domain, so we can form a field of fractions for this as well, UG. And the question is this, does the Gelfand-Kirillov conjecture hold for this family? So recently this was proved by 3 people. I think it's Molev, Futorny, Molev, and Ovsienko. So what they proved is that this is D of M, L of K, where M is the dimension of the centralizer. G is the centralizer of E in this Lie algebra, and L is the rank of G. The rank of G, and this proved that for G of type A. So this is for G of type A. And this can be regarded as a...
Is M, the sum of the dimension of W of Lie algebra and dimension of polynomial algebra? Or it's just Lie algebra part?
No, it's a L, DML. So this involves exactly L variables, free variables.
L variables and M minus L variables from Lie algebra.
M minus L, yeah, I should say, M is not done, yeah, so thank you. So M is equal to, M is equal to dimension of GE minus L over 2, yeah. Where G is the centralizer. So again, this is type A phenomenon, and outside type A, nothing is known. And I should also mention that Ian Gordon proved a version of Gelfand-Kirillov conjecture of certain symplectic reflection algebras related with some semi-direct product, and that symmetric group was involved there, and finite subgroups of SL2. So to me, for myself, the story started when I met Jacques Alev in 2001, I think it was. So one can also formulate the Gelfand-Kirillov conjecture in characteristic P in exactly the same way as in characteristic 0. So say GK is GZ tensor over Z. One can do it actually for all finite dimensional Lie algebras again, but I'm interested in this case. And K is, say, algebraic closure of FP. And then the question is, does the Gelfand-Kirillov conjecture hold for U of GK? There is no need to change anything in the statement because everything is already there. So we have some polynomial algebra still is in here in the enveloping algebra. The Weil algebras are also here. And the statement doesn't require any change. So, and he was interested in this conjecture, and he had a PhD student, Jean-Marie Bois, who is now in Kiel. I think he just started working on this. And so he asked this question, to me. I was surprised. Is it true? So let Z of GK be the center of the enveloping algebra of U of GK. And characteristic P now. Is it true that the field of fractions of Z of GK is rational? So in this case, it means that is it true that it is isomorphic to K of x1, xn? The centering characteristic P is very big because I should say that GK has a restricted Lie algebra structure, so we have P's power map, and then we can have lots of elements in the center. This has filtration degree P in the enveloping algebra, and this has filtration degree 1 or even 0. So this lives in the center of GK for all x in GK. And the subalgebra generated by this is called the P-center. It's a polynomial algebra in n variables, where n is dimension of GK, which is the same as dimension of G, of course. And then, of course, one can look at some examples. And when he asked me, I was surprised. I thought, well, I knew enough about the center, but this was new. So if one can look at the SL2 case. SL2 case is, of course, very classical case, and everything is known about it. And it can be found in several books now. So if you look at SL2 case, so we look at G SL2K, and for this to be simple, well, not actually for this reason, but for a related reason, we assume that characteristic is bigger than 2. Then the center of GK is generated by this element. So we have EHF is of course standard basis. And it's generated by e to the p, h to the p minus h, and f to the p. And by the Casimir, and the Casimir is in this form: 4EF plus h minus 1 squared. There are different ways to write down the Casimir. And so Rudakov and Shafarevich found a nice formula for relating the Casimir with other elements, which is actually a very good exercise. So this product is equal to h to the p minus h squared plus 4 e to the p f to the p. So there is one relation. The center is generated by 4 elements. There is one relation. One can prove that this is a complete intersection in a fine space given by this. So at the level of field of fractions, of course, we can express, so not in the ring, but in the field of fractions, Q of GK, Z of GK is a field of fraction of this, and we can express e to the p, say maybe f to the p, belongs to the subring generated by the Casimir, e to the p, and h to the p minus h. We can just divide by e to the p and subtract this. So it's pretty clear. And so therefore, Q of GK is isomorphic by the transcendence degree argument. Is isomorphic to K of x1, x2, x3. And so the question was, is this true always? And I got hooked with this problem, and I had a PhD student at this time, Rudolf Tange, and I told him about that, and he got hooked. And so we proved this in type A. So we prove this. This is true. Well, one has to be careful for GLN and GSLN when P does not divide N. And I don't know what happens when P divides N. So it is rational. And the argument, in fact, we proved a bit more, is really just playing around this. But the general case remained open. And then using our result, then Jean-Marie Bois proved that he proved that GK holds for GLN and SLN when P does not divide N in characteristic P. So this sorted this case. But again, we didn't get anything new out of it. This was potentially already known. But recently there was a progress. So the reason why one would like to look at the characteristic PK, although it may look exotic, is as follows. So in this case, in characteristic P, U of G, the frac of U of GK, is a division algebra. So it's not a skew field anymore. Well, one doesn't give her this awful names. Now it's a division algebra of dimension P to the power N minus L over this field Q of GK. So since it is a division algebra, one can ask what is a central division algebra. And also Q of GK, I should say, is well understood. The Q of GK is, we just take this P center, ZP of G. ZP is generated by these P powers above. We take invertible elements, and so this localization of with respect to this of ZP, of Z of GK. So we just localize the elements coming from the P center, non-zero elements. And this gives you a description of the field. So if you know that this is rational, then the question is, what is the period of the image of this central division algebra in the Brouwer group of this field, which is, if Alev's question has positive answer, should be field of rational functions. And in type A, from Boas' theorem, and prove that the index of this U of GK in so this is a period in the Brouwer group of Q of GK is P is equal to the characteristic. So it's as small as this could possibly be. In general, this is unknown. So this is open. So this is in type A. Again, follows from a result of Bois, who proved this Gelfand-Kirillov conjecture. Type A, this was proved by Bois. But open in the general case. It's not known what the index is. So there was some progress recently. First of all, Tange answered positively the question of Alev. So he proved that Q of GK is rational for all times. So this was now, so this is now a field of rational functions, so this one can ask these questions. We don't know what the period is. And then I proved recently the following theorem. So if the Gelfand-Kirillov conjecture holds for G, so this is over in characteristic 0 over this field. Then it holds, the same conjecture holds for GK for all sufficiently large primes. And this is a bridge between characteristic 0 theory and characteristic P theory. But then combining this with some techniques in Tange's paper, I proved a bit more. So now, so let say LK be, I should know, so too many. So the strange notation for a field, but K is already engaged. So this be a field extension. So we say that L is pure, Lm is pure, if L is isomorphic to the field of rational functions in some variables, x1, xs, for some s. And then we say the field extension is pure. In birational geometry, people study these problems. They are notoriously difficult problems. So it's like geometrically you can state if you have a fibration, is this fibration trivial? And so these problems also occur in topology, of course. And so using this, I was able to prove that the following theorem. So if the Gelfand-Kirillov conjecture holds over K for G, then then the following extension is pure. Then K of G, the extension K, over the field of invariance here, is pure for all sufficiently large primes. And here GK is the Lie algebra of the semi-simple, simple, simply connected algebraic K group GK. So now this is a classical purity problem, and very recently, G is simple, yes. It's a classical purity problem and was recently solved in characteristic, in characteristic 0. And this is a very recent result by Kaliot, Lem, Kunyavsky, so very recently, hope I got it right. Hope I got this right too. So, this paper is now abbreviated as CTKPR. That's official now. So. And they prove that, prove the following. So, so what did they prove? So over K in characteristic 0, the following are true. So this field extension, now we have K of G over K of the field of invariance. I should say the field of invariance is just polynomial algebra in L variables generated by the Casimirs. So this is not pure. Is not pure if G is of type huh? There is no Q. This is K is the field of regular functions on this Lie algebra. It's just the fraction. So this is fraction algebra of the symmetric algebra on G star.
Okay.
Yeah,
So
it's
and
different.
The same in the theorem?
Oh no, and the same is here as well. Yes.
Okay.
So this K and Q are completely different fields, although they are isomorphic by Tanget's theorem. That's important. So, what? Sorry. K is could be complex number. So K is algebraically closed field. Yeah. Closed field of characteristic 0. Of characteristic 0. And that's very important for their argument. It really is crucial. Because they use, at some point, they use Hironaka's theorem on resolution of singularities. More precisely, they use the fact that homogeneous space has a smooth projective model, which is known in characteristic 0, is to follow from Hironaka. So this is not pure if G is of type B. I have to be very careful here. N bigger than or equal to 3, Dn, n bigger than or equal to 4, E6, E7, E8, and F4. So, and this is the first part. And the second part is, this is pure. So we have is pure if G is of type AN, which was known before, and CN, and this was not known before. And type G2 is undecided in this theorem at the moment. So that's a picture coming from. So they use some characteristic 0 tools. So first they develop a notion of the notion of versality for so-called GS fibrations. And this seems to rely on characteristic 0 argument, but I was able to bypass this. And they also use, at some point, they use the fact that if you have a generic torus in G, they work with generic tori, then it splits over a field whose Galois group is the whole Weil group. This is also fairly easy to generalize. But one heartbeat was that if Gelfand-Kirillov conjecture holds, then this homogeneous space corresponding to generic torus is rational over a base field. And they use this notion of versality, which I was able to bypass. So this also holds. And then, so this leaves us with a final argument which relies on Hironaka, and then this which relies on the fact that homogeneous spaces have smooth projective models. So so let me just not say what this. So T generic is a generic torus in G, where G is now in characteristic 0. Generic torus is just a generic point of the variety of tori, so it's a generic point of G by the normalizer of Ng of T. I should say normalizer of the maximal torus. This variety is known to be rational over the base field. This is an old result of Chevalier, which was later proved by Demazur and Gabriel. It goes back to mid-50s. And this torus doesn't have to be split. So it's a very general result. And we take this generic torus of this variety. We call it T generic. And then we look at this homogeneous space, T by T generic. And this has a smooth projective model. So we have a smooth projective compactification. And then one has some short exact sequences arises involving some Picard groups. And by using some theory, which of course Kaliot-Len knows very well, one is able to prove that if this is rational, so if rational over base field, then using the fact that the Galois group of the splitting field is as big as it could possibly be, then x of t, now t is split now, which is, since G is simply connected, it's just the lattice of weights, can be presented as follows. Can be included in this exact sequence of Galois modules. So the Weil group acts everywhere here. And these are all P1 and P2 are permutation. Permutation modules. And so this argument becomes characteristic free if one knows that this still is true. And one can prove this for almost all prime by base change. So one has to base change this and work over schemes of finite type over there. Then at some point, one has to use a version of Main-Zariski theorem for quasi-finite morphisms. But it seems to work. So, and in fact, there is an interesting problem here. So, so the following fact is, was pointed out to me by Panyushev and Serganova independent. It was in April. So if T is split, then we have an obvious smooth projective model of this homogeneous space. We just take G by B. B is a Borel subgroup containing T, and B minus is an opposite Borel. This is a smooth is a smooth compactification. And so here is a very interesting problem. I think people who like wonderful varieties and things, they might find it attractive. So find such an explicit in any characteristic projective compactification for G mod T prime, where T prime is any. Now it doesn't have to be split, so we cannot find B and B minus over the base field. They just don't exist. For G by D prime, where T prime is any torus in G defined over K. Well, any torus, they're not necessarily split. And a compactification should be defined over the field of definition of T, of course, of T prime. So, yeah, and so as a corollary of this, we obtain that the Gelfand-Kirillov conjecture doesn't hold for in the same cases which occur in CT K PR theorem. So corollary. So the Gelfand-Kirillov conjecture fails for G of type Bn n bigger than or equal to 3 Dn E6, 7, 8, and F4. And there is one interesting thing. In April, Joseph told me that Kirillov told him that the GK holds for G2. For G2. But that's just rumors. But so here we are. Type C. If you ask me, type C and that should hold, I would say. Probably true. And the evidence for this is that this purity result actually holds in type C by the paper of Kalyotel et al. And so the problem is now how can one solve the remaining cases, and since we know that the skew field was more complicated than is more complicated than expected, what are the defining relations of the skew field? They are not relations coming from the Weil algebra, shouldn't be very far away. And so how can one find a nice presentation of this as a division algebra? I guess that's it.
What's the theorem here that you have for P sufficiently large, you can do the CT?
Oh, this theorem.
Well, your version of it.
Yeah, I only proved the part about non-purity result. I don't know how to do it in type C. However, if the Gelfand, sorry?
For all P? Or
For all P very
sufficiently
big.
large P?
I don't know. For all P, because of this thing. It would be true for under very mild assumptions on P if we had explicit smooth compactification of this space, which we don't at the moment. And so there, hence come these assumptions on P. Otherwise, this would hold for almost all for P good, say.
Is there a quantum version of the conjecture?
Yes, there is a quantum root of unity version. By the way, one can also ask question about rationality in the quantum root of unity case, which is not known. I think it is proved by Tange in type A under some by reducing mod P this thing. So he had to impose some assumptions on Q.
But so GK also doesn't hold.
It doesn't hold in characteristic P either.
Actually, that's not question, it's remark. So recently, a guy named Sadetov proved a weakened version of Gelfand-Kirillov conjecture in whole generality. Namely, Gelfand-Kirillov conjecture holds if you allow finite extensions.
That's what Gelfand-Kirillov proved.
No, I mean for all algebras. If
For
you
all.
allow finite extensions.
Oh, this was, by the way, conjectured by Ooms, in this paper, by Alev, Ooms, and Vandenberg. This was posed as a conjecture.
But I believe this result wasn't published. Sadetov, I guess.
Wasn't published.
Yeah.
Well, this result about G2 is not published either. I hope my result will be published.
I propose a break of 6 minutes. We'll start again 10 past and thank Josh again. Thanks very much.